start this. Okay, so in this lecture we're gonna do some Lorentz transformations and all. First of all, let's understand the weird concepts. So before going to the Lorentz transformations. So this is Einstein and this is Lorentz space-time versus ether, and this is Michelson-Morley experiment we have talked about in the previous classes. Okay, so let's do the calculation again. Okay, and it is very easy calculation, you can do very fast also on your own. Okay, so I have this Michelson-Morley apparatus, and this apparatus is moving with respect to ether. Okay, this apparatus is on the earth. Okay, okay. Mm, so this is fine. And suppose this is okay. Draw some. Okay, yeah, it's fine. So this is my apparatus, and cross again. This is my mirror. This is my mirror. Okay, this is some light source. Light will go from here and split by a beam splitter, come back, reflect back from mirror 1 and mirror 2 both. Okay, and just we will detect here. Okay, so this is the lab frame, and this is actually at rest with respect to earth, so we can call it earth frame also, and this is ether frame. Okay, since the earth is moving with respect to ether, we can call it we can denote the velocity of earth with respect to ether as v. Okay, so of course the whole apparatus will also move with respect to the ether. Okay, so let's quickly do the calculation now. So in the like along this uh, suppose I will take these two arms as of equal length. Okay, so suppose this is my along the like arm uh, parallel. Okay, parallel along the motion of apparatus. Okay, or say the S prime frame. Okay, this is my S prime frame, and the ether frame is S frame, and the arm uh, parallel to the motion of apparatus. Let me write it to the parallel to the motion of apparatus, or say parallel parallel to the velocity. Okay, and it is in the x direction, suppose. Okay, so you can calculate the time taken by this light from the beam splitter to reflect from the mirror to and reflect back to the same point again to the beam splitter. What will be the time taken for this case? So you can write it quickly and following the Galilean transformations. Okay, so you will find that the L parallel will be C minus V plus L parallel will be C plus V. Okay, you can recall your Galilean transformations here. Okay, what is it that it is like this? Okay, this is the velocity of S prime frame. This is the velocity of object as observed from S frame, and this is the velocity observed from the S prime frame of an object. Okay, velocity of an object. These two are the velocity of an object, and this is the velocity of S prime frame with respect to S. Okay, so in this parallel arm, you can calculate the velocity of speed of light, velocity of light when it is moving from beam splitter to the mirror too. So it will be like, suppose I am taking the vector notation. Okay, so it will be Cx cap minus Vx cap. Okay, similarly, it is from beam splitter to mirror 2. Okay, similarly, when the beam will go from mirror 2 to beam splitter again. Okay, so you can write it, the velocity transformation is C in the x minus x cap direction, because the light is moving from M2 to beam splitter now, and similarly this will be remain same because the direction of motion is same. So in this case, you will have the C plus V in x cap. In this case, you will have the C minus V x cap. And when you will calculate the magnitude, you will find that one first velocity is C minus V and second velocity is C plus V. Okay, so this is the time measured in the S prime frame. Okay, now fine. So you can see that this can be re uh, framed as like this. Okay, when you like take the LCM and all, this will be like this. Okay, let's assume for simplicity that L parallel is equals to L perpendicular. Okay, perpendicular and parallel to the motion of the apparatus, it is same. Okay, let's assume for simplicity, and I have like assumed in this above diagram also that the both the arms are of equal length. Okay, let's assume this and go ahead. So T dash will be equals to T prime will be equals to this. Suppose, and in the along the like along perpendicular arm, what will happen? It is simple. Like, since my whole apparatus is moving, okay, since my whole apparatus is moving rightwards, then the light will start from here. Okay, then along the when we see the light in the S prime frame, the light will look like it will go from, I mean, uh, it will cover like this, not in the S prime frame. Actually, in the S frame, it will cover like this motion. Okay, this will cover like this. So this is my L perpendicular. In S prime frame, of course, it will look like it will go and okay, not actually. Uh, that's not okay. Let's do it. Okay, so this is my perpendicular arm. Okay, of length A. So in the time, suppose the time taken to reflect back to this beam splitter is T prime 2, and this is suppose T prime 1. Okay, so it will take the whole journey will take the distance, because the speed of light is c, as c t prime, c t prime. Okay, and Suppose in the t2 prime time the apparatus has moved a distance of v t2 prime. Okay, so what will be the hypotenuse? Okay, what will be the hypotenuse? So it will be, I mean, the whole distance covered by the light will be twice of this hypotenuse, and it will be L perpendicular squared plus O v t2 prime by 2 to the whole square. Okay, and you can calculate this, and you will find that t2 prime will come out to be 2L perpendicular by c, and it will be 1 minus v square by c square. Okay, these are my two equations, main two equations. Okay, and this is my another equation. Okay, and of course we have assumed that both of these L parallel and L perpendicular are equal. So the observed quantity was in the experiment. Observed quantity was the difference between two. Actually, like this one, t2 minus t1, this one. So let's calculate, and it was observed to be zero. It was observed to be zero. So let's calculate this t2 minus t1 prime is actually uh, because I have taken like L prime, L parallel equals to L, I can directly write this as the difference between the two. Okay, 1 minus v square by c square. Okay, and minus this. So up to this we have done. Okay, and it should be like 0. Well, how do you explain this phenomena that this should be 0? How can you say that the whole quantity will be 0? How will you justify this in the experiment? So according to Lorentz, okay, first of all, let's take the, you can justify this by taking first of all V as 0. This means Earth is at rest with respect to ether. Okay, this is also called the ether drag theory. Ether drag theory. You can just check when you put the V is equals to 0, then this will be cancelled out. Okay, this is called the ether drag theory, and it was abandoned. It was discarded because later on people have because later on further experiment later on people have done experiments on larger scales. Okay, just hold on for a few minutes because I just want to explain something deeper. We have done these calculations, but I need to explain something. Okay, so let's take this v is equals to 0, and we can justify that v, when the v is 0, when the earth is at rest with respect to ether, then this will whole quantity will be 0. Okay, this is my first theory, first explanation, but it is discarded because later on the people or scientific community have done the experiments on larger scales. Okay, like aberrations of starlight. Okay, these kind of experiments uh, prove that this cannot be true. Okay, now secondly, uh, yes, Lorentz. So here I have just mentioned that Einstein versus Lorentz because they both uh, gave the explanations very well, explanations that are actually theoretically true. Okay, they are theoretically correct explanations. So what was the explanation of Lorentz? So Lorentz said, let's assume let's assume that uh, ether do, okay, let's write it other form. Let's that uh, assume the length of any object is contracted in the direction of motion. Okay, and what is that length here? In this case, in our case, it is L parallel, right? L parallel is the length parallel to the direction of motion. Okay, this was the L, and so contracted means how? Let's assume that L, let's take L dash to be equals to L and multiply with this factor. Okay, we have a factor called gamma in the special theory of relativity, and we denote, we express it like this. Okay, and it is positive, always positive. Okay, it is always positive for velocities. So if it is positive, okay, this, I mean, if it is positive, this implies that L dash is greater than L. Sorry, I have written opposite. L is greater than L. L dash. L is greater than L dash. Okay, so if we assume this, so you will see that what will happen. You will assume this, what will happen, that here you will replace it by L dash. Okay, here you will replace it by L dash, and you will keep here the L perpendicular because there is no effect in the perpendicular direction. Just keep it here. So you will find that T1 dash will be equals to 2L prime by C. Okay, and you will find that this will be equals to 2L 1 minus V squared by C squared by C 1 minus V squared by C squared. Okay, and you will see it will be 2L by C, and it will be 1 minus V squared by C squared, right? Okay, so it's my third equation. Similarly, you do not have any effect in the direction of motion according to Lorentz. So you will have the same thing here. Okay, you have the same thing here because L perpendicular is also L. We have assumed it, so this will implies that del t equals to del t prime minus del will equals to 0. This was the explanation given by Lorentz, and you see in the S frame, calculate the time in the S frame. Can you calculate the time? It is very easy because there is no effect of motion. In the S prime frame, speed is not changing. Okay, remember this every factor of gamma is arising due to the change of speed while translating our physics from one reference frame to another reference frame. Okay, it is due to the changing speed, not anything else. So in the T prime S frame, okay, sorry, T in the S frame, the T will be, you can guess it from here. There is simply in S frame, the speed of light is constant. So it will move. What will it? Uh, what will the time taken by the light? It will be simply 2L by C. You can check it. Okay. to L by C. In the parallel, I mean also parallel to the motion, and also it will be same as perpendicular to the motion. It will be same. So you can write it like this is same thing. This is same thing. Okay. So actually the T1 prime is equals to T2 prime equals to, it will be 1 minus V squared by C squared and times T times T. So from here you can generally write like this, 1 minus V squared by C squared. Okay. This is called time dilation. This is called time dilation. And what is this called? This is called length contraction. Okay, this is called length contraction. Now let's collect what we have done. So according to Lorentz, okay, we have some transformations like this. Okay, for length and time, like in the parallel motion, my L parallel is get contracted. Okay, in the perpendicular motion, there is no effect. Okay, and my T prime is being dilated. Then we can justify or reconcile with the results of Michelson mold experiment. Okay, but these these equations are arising actually from the from like changing speed of light, changing speed of light. Okay, changing when moving when moving from one reference frame to another, it should be inertial. Okay, inertial reference frame. Okay, so it actually saves the ether theory, because according to Lorentz, these length contractions and time dilation kind of thing occurs due to the motion of object through the ether, through the ether. Okay, because according to Lorentz, these length contraction and time dilation kind of things occur due to the motion of object through the ether. Okay, and you see this is these gamma factor is arising. You see the gamma factor is due to again change in speed, change in speed, or say different speeds, different, I should write it again, different speeds of light and different inertial field. Okay, but it was This theory is correctly describing the Michelson-Morley results. Okay, so but the thing is, this theory is discarded. Why? Because it assumes it also like uh, tells you that tells you that you can never detect ether. It also tells you that you can never detect ether. So this is the thing that raised the question, many questions regarding ether. Actually, it's uh, good to like justify the ether, but there are more questions now. What is ether? Now there are more questions. Now there are more questions. Questions. What is this ether? What it is? What is it made of? How uh, the motion through it leads to length contraction and time dilation phenomena. Phenomena. Okay. And secondly, the problem is we cannot even detect its properties. The thing is, the problem is this. There are more questions now. But Einstein gave some simpler solution. Einstein gave some simpler solution that let's just assume that speed of light is constant in all kind of inertial frames. All kind of inertial frames. Okay. There is just this assumption taken by Einstein, and time dilation and length contraction, say, and length contraction and time dilation. This thing will also occur in his theory, but as a consequence of this assumption, that is constancy of speed of light. Okay, constancy of speed of light. So there is a question like why? Okay, let's come to it later on. Of course, you can. Of course, you can. Of course, you can ask the question. The question: what if Lorentz is true? Lorentz theory is true. What if Lorentz theory is true, and there really exists some ether? But in science, but in science, we follow the explanation. The simplest explanation. Okay, there is some principle that is Occam's principle in science. or we also say Occam's razor principle that tells you that when two well established theories have equal explanatory power and capability to predict same things, we prefer to choose theory with less number of assumptions assumed to establish it. Okay, this is the principle. We follow some scientific methods. Okay, this is scientific principle. When two well-established theories have equal explanatory power and capability to predict same things, we prefer those theories that have less number of assumptions assumed to establish it. So Lorentz assumed, Lorentz assumed what kind of assumptions? What kind of assumptions? First of all, he assumed absoluteness, absoluteness of space and time. We assume that space and time are absolute, but the motion of object through the ether do actually lead to length contraction or time dilation kind of things. He introduced the concept of local time, that locally we do always have this absoluteness, and also globally we do globally also we do have this absoluteness, but through the motion of through the motion through the ether do actually changes affect the space and time. Okay, let me write it again. So let's do it faster so that we can complete our Lorentz transformations also. So while moving from S to S prime free, according to Lorentz, okay, space and time will be disturbed. Okay, let me write not space and time. Space and time observations will be disturbed due to motion through the ether. Okay, and produce null effects in Michelson-Morley experiment. Till now, if you have any question, you can ask. Okay, and according to Einstein, okay, space and time observations will be disturbed, okay, due to I mean to maintain speed of the constant speed of light. Okay, of course, in different inertial frames, and similarly, and produce same null effect in Michelson-Morley experiment. Okay, we will see that what were the assumptions. Okay, so the simpler assumptions by Lorentz assumed, first of all, absoluteness of space and time. Secondly, he assumed existence of mysterious ether that cannot be detected. Third, he assumed length contraction. Fourth, he assumed time dilation. So these are the assumptions that Lorentz actually assumed. But Einstein did not assume these kind of things. Okay, Einstein did not assume these kind of things. Okay, you can also include the principle of relativity here. Principle of relativity. So Einstein, of course, assumed the principle of relativity. Okay, and secondly, he assumed constant speed of light. Constant speed of light. And you can say he assumed like relativity of space and time. He assumed that space and time are relative. But these two things and plus these ether thing, he did not assume. These are the extra things that Lorentz assumed. Okay, length contraction, length contraction, and time dilation are consequences of these assumptions in Einstein theory. Okay, length contraction and time dilation are the consequences of these assumptions in the Einstein theory. So Einstein gave simpler explanations. Nice. So Einstein gave actually simpler explanation for Michelson-Morley experiment results, or say null result. Of course, of course, we are not disproving Lorentz ether theory, but we are abandoning abandoning it based on scientific principles. And it is natural. Okay, it is these things. This Occam's principle is natural. Suppose if you have a vendor, okay, if a vendor you buy an ice cream, okay, from a vendor that is far uh, from your home. Suppose it is like 1 kilometer away home from your home, and you buy an ice cream, and you come to home and just put it in the refrigerator at night, okay, and you just found, like in the morning, that you found that there is no ice cream, okay, in your refrigerator. So what will be your first reaction towards it? That what will you assume? You will assume that maybe the most irritating person in your home, that is your brother or sister, may have like ate, ate it, okay, may have taken the ice creams. And you will not assume, actually it is natural thing that you will not assume that the vendor itself has come to your home and taken the ice cream. That is natural thing that you will assume. So what is the simpler explanation that your ice cream is like not present in the refrigerator in the morning, and you will go for the simpler explanations that you must follow, that you will assume. So Occam's principle is like, it's a natural principle that we will follow in science. We do follow actually in science. Okay, so that was about the thing. And there is a question. We will do like Lorentz transformation quickly, but there is a question you must be asking. Okay, why there? I mean, in both theories, whether ether exists or not, in both theories, you will see that time dilation and length contraction kind of things is happening in both theories. But why? The length contraction in the parallel direction only, not in the perpendicular direction. Of course, the time is dilated when we translate our physics from S frame to S prime frame. Okay, but why the length is not contracted in the like perpendicular direction, and why one is contracting and one is dilating? That is another thing. And why there is change in length and time? So, suppose in the Einstein theory, if I say the like in Einstein theory, we have to maintain this constancy of speed of light. Okay, we have to maintain the constancy of speed of light. So, like constant speed observations is equals to distance observations distance. Let me write it. Distance observations divided by distance observation divided by time observation, right? And suppose if you contract the distance, okay, we have to maintain this constancy. So if you are varying, disturbing the distance, then the time should disturb also. Okay, if you are suppose uh, making your L to some gamma L, so this will imply your time will go from uh, T to T by gamma. This is obvious from this to maintain the constant speed observation. Okay, in all inertial frames. Okay, you understand this, why the length is contracting and why the time is dilating. Okay, if in while translating our physics from one frame to one inertial frame to another, if your distance is contracting, this implies that time must dilate. Okay, so this is obvious from this. Now, why the question is why there is only contraction along parallel direction, or say uh, length contraction along parallel, not along, parallel to the motion. Okay, parallel to the motion. Why? To maintain, it is to maintain consistency in theory. Just to maintain the consistency in the theory. Like for example, suppose you have a train. Okay, suppose you have a train. Okay, moving with some velocity that is equals to root 3 c. Okay, c is the speed of light, root 3 c by 2. You will find that the gamma, which we have defined like this, okay, it will be uh, it will be greater than 1 always, and it will be equals to 1. It will be equals to 2. Okay, and suppose the height is 5 meter of this train, and this train is approaching a tunnel here. Okay, let me make this tunnel somewhat bigger. Okay, and it has a height of 8 meters. Okay, this tunnel, this is my tunnel, this is my train. Okay, and of course this is moving, and this is the rest. So when you will see, suppose length contraction occurs in direction perpendicular to the direction of motion. Okay, if because you see, the theory says that there should be length contraction only in the direction of motion, not in the perpendicular of the motion. But if we assume that length contraction occurs in the direction perpendicular to the direction of motion, that is its height. Okay, its height, then from one frame you will see, sorry, like from the tunnel frame, from the stationary frame, that is tunnel frame, we will see that train's height will be contracted. Train's height will be contracted, contract to 2.5 meters. Okay, when you apply the contraction formula, okay, or expression, train's height will contract to, but in S prime frame, that is train frame, you will see that tunnel's height, tunnel's height will contract to 4 meter, will contract to 4 meters, and you see that physics is inconsistent. You see, physics is in, inconsistent. Let me write it again. Physics is inconsistent. Okay, why? Why physics is inconsistent? You see, what is the inconsistency here? That is both in both frame, I mean, in both frame, the the observers should agree on events, but here they are not agreeing. I mean, agree not agree on same event, but they are not agreeing in this case. Why? Because the train is of 5 meter. Okay, in S prime frame, the tunnel's height is reduced to 4 meters. Okay, so what will happen? In tunnel frame, there is a destruction. There is a destruction because how can a 5 meter tall train, be fit into the 4 meter tall uh, tunnel? So in S prime frame, there is a destruction. But as you see from S frame, as you see from the S frame, that uh, yeah, as you see from the S frame, that is the tunnel frame, the train height is contracted to 2.5 meter, and of course the train will pass through the tunnel. Okay, there is collision. Okay, no destruction. There is no collision. So events are changing when you are seeing the same event. I mean, you are seeing the different events when you are translating your physics from one frame to one inertial frame to another. So this is physically impossible. Okay? This is physically impossible task. Length contraction cannot occur in the direction perpendicular to the direction of motion. Okay. So I will take just few more minutes. Okay, to derive uh, the Lorentz transformations. First of all, let's give some postulates. Let's start our spatial theory of relativity now. Okay, and it starts with two postulates. Two postulates of Einstein of spatial theory of relativity. That is, first is itself the principle of relativity. Okay, that is, all laws of physics must be same in all inertial frames of reference. Okay, this is my first postulate of SR. Second postulate is constancy of speed of light. These are the only two assumptions. Okay, constants of speed of light. Then we can derive the whole spatial theory of relativity. Speed of light is constant in all inertial frames of reference. Okay, so these are the two postulates. You must remember it, and they are important postulates, and anyone can ask you about it because these are the fundamental postulates. So let's go further. Lorentz transformation. It will not take much time. Okay, Lorentz transformation. Okay, Lorentz transformations was originally like introduced by Lorentz, but it can be, these transformations can also be like derived from just these two postulates of Einstein. Okay, suppose there are two frames. Okay, again that is S and S prime frame. This is X, this is Z in left hand coordinate system. Okay, this is my S frame and this is my S prime frame. Okay, and it is moving with respect to this S frame with velocity v. Okay, now we will consider four cases. We will consider four cases. Case 1, event is happening, event E is happening or occurring, I should say, occurring at origin of S frame. Let's say, yeah, origin of S frame. Second case, event is occurring at origin of S prime frame. Okay, motion of light, motion of light in X direction, that is parallel to the motion of S prime frame. Okay, and fourth case, motion of light in Z direction, perpendicular to the motion of S prime frame. Okay, parallel to S frame motion, and this is perpendicular to S frame motion. These are just four cases we have to analyze quickly. Okay, suppose let's take the first case, case 1. Okay, my event is occurring at the origin of this S frame. Okay, event is happening here, case 1. So what will be the coordinates now? Can you tell me what will be the coordinates in S frame? Suppose first of all in S frame, case 1 in S frame, event is occurring at the origin of S frame. So what will be its coordinate? X equals to 0, right? And then we will have the coordinates. And what about like uh, okay, just wait a second. Okay, first of all we have to assume something, then we will consider. Okay. Assume something that is called ansatz. Let's take some ansatz that are Lorentz transformations, Lorentz transformation equations should look like Lorentz transformations equations should look like T prime should be A. We are just considering the general case. Plus Bx x prime is equals to dtx plus fx. Okay, y prime equals to y. Because the motion is in the x direction, we assume the changes in the x coordinate. Okay, and we are not considering any t square kind of terms because it will lead to non-inertial forces. You can check it. Okay, so we just consider the general Lorentz transformations as these, and we will now find these coefficients. Okay, there are four coefficients, and we have the four cases. We have the four cases and four coefficients. So, of course, we will find the possible solutions for these four coefficients. Okay, so case 1 is, what is the case 1? Event is happening at the origin of S frame. Okay, so what are the coordinates here? X equals to 0. is equals to 0 and x prime is equals to minus vt. Of course, when you see from s prime frame, the event is happening at a distance of minus vt prime actually. It is minus vt prime because we are in the s prime frame. Okay, so what will happen to our equation? Mm, let's do it opposite way, so it will be better this way. Okay, let's do the first. Let's have the s prime frame. Okay, let's have the s prime frame. The first case, the event is occurring at the origin of s prime frame. So according to this, my s coordinate will be vt, that is, sorry, x coordinate, and x prime coordinate will be 0, right? You can say from it here, if the event is happening at the origin of s prime frame, my x coordinate is vt, because this s prime frame was initially at this origin. Consider, okay, you can assume both origin, okay, that is o and o prime were coincident initially. Okay, we can assume both origins are coincident initially. So after t time in s prime frame, it will move, the s prime frame will move towards right. Okay, so x coordinate will be vt, and in the s prime frame, x prime coordinate will be 0 in this frame. So it is simple. Now put these constraints in the above equations. It is easy that you will find be this, it is 0, and so it will be like this, and of course these won't change, these won't change. So what will happen according to this one, your dt will be equals to fx, right? This is my first, let me write it in Rome. Okay, now next case, case 2, quickly. The event is occurring in the s frame. Now the event is occurring at the this origin, o origin. Okay, so according to s frame, the x coordinate will be 0, and according to s prime frame, the coordinate of this event will be minus vt prime, right? So similarly, x is 0 and x prime will be minus vt prime. Okay, put this in the above equations. So there are two x here. Okay, there are two places where x has to be put to 0, and there is one equation where x prime has to be put like minus vt prime. So let's put the x prime. Okay, it was dt my plus fx. So this will lead to minus vt prime equals to dt plus 0, right? So you find that dt prime equals to minus v d, sorry, d by v and t. Okay, now the other thing is, other equation is t prime, and you will put the 0 in the x equals to 0 in the t prime equation, and what will it be? Then it will be, now you just compare both of these equations. Compare, what you will find that a is equals to minus d by v, right? Is it correct? dt is equals to minus of fx. Wait a second. And also we have to put something else here. We have not put the vt part. Okay, in this case dt will be equals to minus of vx, which is also equals to minus of vt, because we have x coordinate as vt. So now you can cancel out the t part, and you will find that d is equals to minus fv. This is the first relation. Okay, now in the second case, what will happen? This is fine, and you can now replace it with f. Okay, so this will be f using equation first, f t, right? It will be equals to ft, and you compare both of these now. Compare both of these equations. Okay, this equation is arising from x prime, and this equation is arising from t prime equation. Okay, these are both different equations. These are Lorentz. First one is arising from this equation, and second one from the above t prime equation. Okay, now you compare both, and you will find that these a and f are equal. Okay, you will find that a and f are equal. This is my second constant equation, right? Now from these constant equations we have reduced some coefficients. Okay, now rewrite these equations. What we have by using these constant equations. So rewrite we can rewrite Lorentz equations as, what will be the t prime, now. No, there is something else, I guess. Yes, it is correct. Okay, let's write. We are going the right way. Okay, so my equation will be a t plus bx, and x prime will be, here it was d, and we have replaced d with minus fv, and we know f is a, so we can write minus av using both equations. Okay, plus there was f, and we know we can replace it with ax, and there is also a time coordinate, so there should be a time here. Okay, so these are my now new equations. Okay, these are my new equations. We have reduced, using two cases we have reduced our number of coefficients to 2. Now we have two other cases, 3 and 4, and we have to just find these two coefficients also. So let's consider the motion of light in the x direction. Motion of light in the x direction. Case 3, motion of light in the x direction. So suppose the light is originating from this O prime, O origin. Okay, so in t time, it will cover some c distance. Okay, light light originate at x equals to 0 and travel along x direction, suppose. Okay, so what will happen? My x coordinate will be ct after t time, after time t. Okay, x coordinate will be ct, and what will be the coordinate of x prime? What will be the x prime? In its frame, we have assumed by second postulate that the speed of light is constant. So, sorry, I must write it here in the next line. Okay, that is an S frame. Okay, in X prime frame, it is C T prime, right? So because of second postulate. Uh, in both frames, the speed of light is constant. Okay, so what will happen to our equations? Let's use this equation. Let's use this equation and put our translated and transformed equations. What is x prime here? It is minus of vt plus ax. Okay, is equals to c times t prime, right? So you can also write it as x minus vt as c into this. Okay, you can write it as minus cat c dx, right? Take out the a common, you will find x minus p minus ct and c dx. Okay, you can write it as c minus v or c plus v t equals dx, and you will relate it like c dx on x minus c plus v t. But we have also assumed, not assumed, but we also know that x coordinate is ct. Since x is ct, then this, so a equals to c square bt upon x is ct minus ct minus vt. Okay, so this will be cancelled out, and t there will remain, t also will be cancelled out from the above t, and we will have a equals to c square b minus and b. This will be our third constant equation, right? Now you have, like, you can write it as like this also, this c squared, you replace it in these equation, and what you will find, again rewrite equation. Okay, Lorentz equation can be now written as t prime as a t minus v by c squared, and here it will be x because we have replaced, and there will be a also. Okay, now x prime will be, what will be, it will be a minus vt and plus ax. Okay, you can further write it as a t minus v by c squared x. You can further write it as x minus vt. Okay, and y prime is equals to y and z prime equals to z. Now these are the Now we have remaining one case only, that is the motion of light in the z direction, that is perpendicular to s prime frame, s prime motion. And we will just knock down this a factor also, a coefficient also, use the fourth case, and then we will have the Lorentz transformation equation. So along the perpendicular motion, along the perpendicular motion, suppose my light is originating from this O origin and it is traveling in this. Okay, my third case was my light was propagating in the x direction. Now my light is propagating in this z direction. Okay, so in this z direction, what will be my z coordinate? It will be, after some t time, it will be ct, of course, and similarly the height will be same in the s prime frame. Okay, you consider this origin is at the same level of this O prime. Okay, here I have drawn something wrong, but you can consider. Okay, let's redraw it quickly. It won't take much time. It is at same level. Okay, you can consider this Y prime. This is X prime. Okay, this is my O prime. Now it is fine. So it is of same height. So Z will also be CT dash in this frame. Okay, but what about X other coordinates? The thing is, in this coordinate, light, I mean in this frame, the light is traveling in this z direction here, okay, at x equals to 0. But in s prime frame, since the s prime frame is moving in the right direction, it will observe this light not as a straight path, but with a like a triangular path. Not a triangular path, but as a slanted path, because it is moving. You just imagine, okay, you just imagine, you can just see it, you can just observe it. Suppose initially my two frames are coincident. Okay, suppose initially my two frames are coincident, and a light is emanating, is going in the above direction. So let the s frame remain here in this uh, system. Okay, now translate your s frame. Okay, now translate your s frame. This is x, this is y, this is z. Now translate your, this is s frame, your x frame, s prime frame, with some velocity v. Okay, you were standing here, origin, seeing this light. Okay, imagine yourself in the s prime frame, and suddenly this s prime frame start to move in the rightward direction. What you will see, some motion, the light will travel like this in this frame, in s prime frame. The trajectory will be curved. You will observe this. Okay, you can observe this with a ball thrown upward also, and you are in the train. Okay, a ball is thrown, suppose at a station. At a station, someone throws a ball upward. Okay, and you are in a train, and you will find that the ball will follow some kind of this kind of trajectory. Okay, when you are in the train. Okay, so it is simple to see this. So what will happen, that I will have this kind of structure in S prime frame. Okay, where my light is going like this. So this is my Z prime equals to CT prime. Okay, this is perpendicular, and this is of course my VT uh, prime coordinate. Uh, yes, VT prime coordinate in the S prime frame, and this will be my CT prime to the whole squared and vt prime to the whole squared, right? So this is my the path covered by the light. So you can say in both frames, uh, like we have this x coordinate, not the x coordinate actually, the x prime squared plus z prime squared will be equals to c t prime. If I'm correct, this is my, but I need to know my x coordinate. No, this will not be like this. I need to find the my x x in the s prime frame. My light will yes, due to the second postulate again. Due to the second postulate, my speed of light is constant, and you will see that my I'm just confused here. Okay, let's go and we'll tell you after this class what is the issue here. Let's assume this it is z prime and this is x prime, and the coordinate is this is traveling with the speed of light. Okay, and the time is t prime in the t coordinate, so you can write this equation. uh, or sometimes happen I forget some things. Okay, let's rewrite these things, and z prime will be now, okay, in this frame we have x equals to 0 and z equals to ct, and of course x prime is equals to minus vt prime, and so I was right actually. C prime is same height of same height. Let's do this. Ct prime is equals to this, and my x prime will be minus t prime squared plus c squared t prime squared. Okay, and so what will it be? Minus v squared t prime squared plus c squared t prime squared, and you will find that after taking the common, you will see c squared minus v squared. This is my z squared. Okay, now of course my z is you can take it out, you know, minus v squared by c squared, and this is my z prime squared. Now take this out, and you will find, okay, you put this condition z prime is equals to ct, okay, z prime equals to ct, you will find this, wait, and yeah, there is square. Okay, you will find this kind of equation that t prime is equals to 1 upon 2 over t, and we have considered this event at x equals to 0. Okay, now take your this equation. We have rewritten this equation. Take the t prime equation. When you consider an event at x equals to 0 that we have considered in this fourth case, write this x is equals to 0, and you will see that t prime will be equals to t at. In rewritten equations, you will see that t prime is equals to at when x equals to 0. So you finally found that a is equals to minus 1 by c squared by v squared. Okay, so my reasoning was correct, but there was some issue. Okay, I will get back to it in the next class. But for now, we have knocked down all the coefficients. and we have found the transformation equations. Okay, so my first coefficient is a, which is 1 minus b squared by c squared. Okay, and there was no other coefficients remaining in the rewritten uh, this equation. So you can now rewrite this equation. Okay, because my a, let's, and this is my gamma, we have introduced it earlier also. Okay, just it is just a notation you will find in many books. So my equations are now, this is gamma equals to t minus v by c squared x. X prime is equals to gamma x minus vt. Y prime is equals to y and z prime equals to z. And these are called the Lorentz transformations equations. Lorentz transformation equations of SR. These are the few of the master equations of special theory of relativity. Okay, now uh, we have to symmetrize something. Okay, now let's multiply c in equation, in t prime equation. Okay, so we will have this as ct prime as ct minus v by c x, and let's define v by c as beta. So this will imply that gamma is actually 1 minus beta squared. Okay, gamma will be actually 1 minus beta squared. And the second equation, we can rewrite it as x minus v by c into ct. Okay, so you can rewrite this as beta. Okay, and you can rewrite this 2 as beta x. This is beta into ct. Okay, you just need to now define your 4 vector, that is 4 components with 4 direction. We have already introduced in the first or second class. Okay, 4 vector is like x coordinate, right? Like this is time coordinate. We usually consider this is the time coordinate, and these are 3 spatial coordinates, and these are just the components of a 4 vector. Okay, let me write it. Okay, it will just take just 2 more minutes. Okay, we can define a 4 vector as this is. Okay, I have introduced this notation before. This is a 4 vector. Let's write it like this. This is the my time coordinate. This is my first x coordinate. Okay, and this is my third y coordinate. Sorry, this is my y coordinate. This is my z coordinate, suppose. Okay, so this is how I define my 4 vector, and the coefficients can be rewritten as 1, 2, and 3 can be given by like ct x y z. These are equivalent to these. Okay, where my time coordinate is actually my ct. Okay, so these all are distance, and if you consider t as time, c as speed, so these all will carry the dimension of distance. So you can rewrite these equations in more symmetric way, like I have written already, as this, that x0 prime. Okay, let me write it. This x0 prime is gamma x0 minus beta x1 and x1 prime is equals to gamma x1 minus beta c, that is beta again, and x0, you can check it, and these two are same, and you can define just a matrix out of it in matrix representation. Okay, this is x0 prime, this is x1 prime, this is x2 prime, this is x3 prime. You can just write it down. What will be the matrix looking like now? It is simply gamma minus gamma beta minus gamma beta. Okay, gamma 0 0 0 0 0 0 0 1 and 1, and there is another 0, and this is my old coordinates. Okay, where of course this is ct prime and this is ct prime, and this coordinate is ct. Okay, so, and I can name it just like before we have done in the Galilean transformation. We denote it now by a lambda. This is most useful notation. Not useful actually. It is a defined notation, standard notation for Lorentz transformations. Okay, in the standard books you will find it. So I can write any 4 vector like this as when this this is called lambda, capital lambda, and this is my coordinates in S frame, and this is S prime frame. This is how you do, and it's simple again, just like Galilean transformation. Find my inverse Lorentz transformations. This is Lorentz transformations formation matrix. Okay, let's now end this class. You just have to find the inverse Lorentz transformations, just as you found the inverse Galilean transformations. Inverse Lorentz transformation matrix. Okay, so these are my equations. You just remember these are my main equations, where my x naught is ct prime. Okay, so if you have any question you can ask. We have ended our class here. Okay, fine. Let's end this class.